Welcome to this explainer. Today, we're going to tackle a massive performance bottleneck that's literally sitting inside the computer or smartphone you're using right now. We're diving into a fascinating paper from the Laboratory for Computer Architecture, and they're using something called highly efficient weightless neural networks to solve a really critical issue in microprocessor design. It's a game changer for sure.
Okay, so here's our roadmap for today. First, we'll look at the branch prediction bottleneck. Then, the neural hardware overhead. Third, how weightless networks come to the rescue. Fourth, exactly how Wizard predicts these branches. And finally, how it manages to beat the state-of-the-art. Let's get right into it.
Section 1. The branch prediction bottleneck. So, to really understand this elegant solution, we first need to establish why conditional branches are such a massive headache for modern superscalar processors in the first place. You can think of conditional branches as literal forks in a train track for your CPU. In high-level programming, these are your standard if, for, and while loops. Now, because modern processors are incredibly fast and heavily pipelined, they absolutely cannot afford to just stop and wait at this fork to figure out which way the train should actually go. Instead, they use a branch predictor to speculatively guess the correct path, sending instructions down it immediately. And keep in mind, branch instructions are super common. They make up roughly 20 to 30% of all computer program instructions. If the processor guesses the right path, execution is seamless, it's lightning fast. But if the predictor guesses wrong, that's a misprediction. The CPU has to slam on the brakes, flush the entire pipeline of all those speculated instructions, and start completely over on the correct path. As you can imagine, this wastes an immense amount of time and energy.
Which brings us to Section 2, the neural hardware overhead.
Because getting these predictions right is so absolutely critical, the industry has naturally turned to machine learning to make better guesses. But right now, the current gold standards, like variants of the Tage predictor and perceptron-based neural predictors, well, they come with a massive catch. Yes, they're highly accurate, but traditional neural networks like perceptrons rely on incredibly complex weighted math and massive input sizes. Take the state-of-the-art multi-perceptron predictor, for example. It requires huge input sizes just to separate the data effectively, and the math involved, it eats up a lot of processing power. In the microscopic world of microprocessor design, complex math and massive inputs mean you need massive silicon real estate. So you're basically trading one bottleneck for a huge area and energy overhead problem. What chip designers really need is the holy grail, an ideal predictor with the high accuracy of a neural network, but with a small input size and absolutely zero complex arithmetic.
Section 3. Weightless networks to the rescue.
This hardware overhead problem perfectly illustrates why researchers have introduced a completely novel architecture to CPU design. Enter weightless neural networks, or WNNs. They are a really fascinating subfield of machine learning. You know how conventional artificial neural networks are inspired by the brain, relying heavily on weighted sum and threshold math to simulate synapses? Well, weightless networks take a slightly different biological inspiration. They actually prioritize the dendritic tree structure of the neuron. So instead of doing complex calculus to adjust weights, a WNN uses RAM nodes. Think of these as essentially simple memory lookup tables. This means the model can learn highly complex, nonlinear functions from its inputs without doing a single heavy arithmetic operation. Literally, it just looks up a value in a table. How cool is that?
The specific model the researchers adapted here is called Wizard, which stands for Wilkie, Stoneham, and Alexander's recognition device. Fun fact, it was actually the first weightless neural network to achieve commercial success years ago. In this microarchitecture context, the Wizard model treats branch prediction as a straightforward binary classification problem. Basically, is the branch taken or not taken? It tackles this using a highly elegant one-shot online training methodology. It's just 3 steps. First, it reads the input features. Second, it uses those features to address the RAM node. And third, it either updates an access counter during training or generates a response during classification.
Moving on to Section 4, how Wizard predicts branches.
Let's trace exactly how Wizard makes these predictions without using any of that heavy math. Imagine looking inside one of these RAM nodes during the training phase. Picture a stream of binary data coming in from the CPU. The Wizard predictor takes a chunk of those input bits and simply uses them as an address, kind of like a zip code. It goes directly to that specific slot in the RAM node's lookup table and increments a counter by 1. That's really it. There are no complex weight adjustments. It's just adding a tally mark to a specific address based on the input pattern. And to prevent those counters from maxing out over time, the system uses a clever bleaching algorithm that sets a threshold. If the counter is above the threshold, it outputs a 1. If not, it outputs a 0. Now, obviously, a single RAM node isn't going to be enough to make a highly accurate prediction on its own, so multiple RAM nodes are grouped together into what's called a discriminator. You'll have one discriminator specifically trained to recognize patterns when a branch is taken, and another one trained for when it is not taken. During the classification phase, which is when the CPU actually needs a prediction right that second, the input bits are fed into the RAM nodes, and each node outputs its binary response based on what it learned. Then the discriminator simply adds up all the ones from its RAM nodes. The discriminator with the highest total sum wins, and that winning decision is the final prediction sent straight to the CPU's instruction fetch unit.
Of course, to make this work accurately, you've got to feed the network the right kind of data. Crucial CPU variables like the program counter, which tells us where we currently are in the code, and the global history register, which tells us the outcomes of recent branches, are linearly combined. They even use a super simple XOR logic gate to merge some of this history together efficiently. This specific cocktail of microarchitectural information forms the binary input that feeds directly into those highly efficient YSAR discriminators.
Section 5. Beating the state of the art.
When we look at the experimental data, all this elegant logic builds into an incredible advantage. The researchers put their network to the test against the current heavyweights, the Tajay SCL predictor and the multi-perceptive perceptron. They ran them across all sorts of different datasets, representing integer, multimedia, and server workloads. The crucial takeaway here is that the WENN completely matches the state-of-the-art Tajay predictor at roughly 96% average accuracy, and it outright beats the multi-perceptive perceptron. But here's the true victory. Remember how we talked about overhead? Well, the Tajay and perceptron models require massive input sizes of over 3100 and 2300 bits respectively. The WNN achieved this winning accuracy with an input size of just 2158 bits, so it's getting the same or better results while utilizing vastly simpler hardware logic.
And honestly, the results get even more impressive. The researchers ran a sensitivity analysis to see what would happen if they tuned the input parameters specifically for certain types of applications. When they optimized the wizard-based predictor for the M2 multimedia dataset, the specialized predictor didn't just match the state-of-the-art, it outperformed it by more than 2.3%. Now, in the everyday world, 2.3% might not sound like a lot, but in the world of microprocessor design where you're dealing with millions of branches being executed every single second, a 2.3% leap in accuracy without the complex arithmetic overhead is an absolute game-changer for performance and power savings.
This brilliantly simple architecture proves a vital lesson for the future of computer hardware. Bigger isn't always better. By relying on the elegant logic of lookup tables instead of heavy, power-hungry mathematical weights, the WISARD model delivers world-class accuracy while respecting the strict physical limits of silicon design. It really leaves us with a thrilling question to consider. If weightless networks can revolutionize branch prediction, what other deep-seated microarchitecture bottlenecks could we solve by simply dropping the weights? Thank you for joining me on this explainer, and I hope this sparked your curiosity about the incredible invisible architecture powering our digital world.